Good evening. Welcome to the second review session. As usual, please feel free to jump in the chat with any questions or suggestions about topics you'd like me to cover. But I'm going to start off by working through the definite integral Dominoes activity that you probably did in class recently. This is just a lot of really good practice evaluating some definite integrals using the second part of the fundamental theorem of calculus. So let's dive in. I guess the top part of each domino is an integral, so we're going to evaluate these integrals. Some of them just match with a graph. They don't have the number appearing on a domino, but whatever, we'll compute all of these definite integrals. And we'll see whether there's a number or a graph that matches with it. Okay, so this first integral, you have to do one step before you find an antiderivative, which is that, well, you might be tempted to say that an antiderivative is 1/2 x squared plus x times 1/2 x squared minus 1, but this is not an antiderivative of x plus 1 times x minus 1. The temptation is to anti-differentiate each factor, but the product of the antiderivatives is not going to be an antiderivative of the product. For the same reason, essentially, that the derivative of a product is not the product of the derivatives. We need to use the product rule when we differentiate. So how would I find an antiderivative? Well, I would just first expand out the integrand. If I FOIL this out, I get x squared minus 1. An antiderivative for that is going to be 1/3 x cubed minus x, and I evaluate from 0 to 1, which means I plug in 1, and I plug in 0, and I subtract the results. So this comes out to 1/3 minus 1, this is all 0, and we end up with minus 2/3. Alright, so this was domino letter A. Let's see if there's a minus 2/3 somewhere. Yep, there is, right here. So this one goes with domino A. Okay, so let's stick with this domino and let's see where this one matches up. Now pi is a constant, so an antiderivative for pi is simply pi times x. When I use the fundamental theorem of calculus, I just end up with pi. Is pi one of the answers here? No, I don't see that, so it must be a graph. It's this one. We're integrating from 0 to 1. My x values go from 0 to 1, and the function I'm integrating is the constant function pi, and that's exactly what I see here. The constant function, which is at pi, which is about 3.14. And this is such a simple integral, you don't really even need the fundamental theorem of calculus. The area underneath that curve is just a rectangle. And the rectangle's area is base times height, 1 times pi, which is pi. Okay, so this one matches with J. Now how about the the integral from 0 to 1 of the square root of x? To anti-differentiate this, it's going to be easiest if we rewrite the square root of x using an exponent of 1/2. Okay, so I'm looking for something whose derivative is x to the 1/2. I know that when I differentiate a power function, the exponent drops by 1, So I'm looking for something like x to the 3/2, because when I differentiate that and I subtract 1, it'll drop 3/2 down to 1/2. The problem is, the power rule says when I differentiate x to the 3/2, I get 3/2 x to the 1/2. And there's no 3/2 in front of that x to the 1/2. So what do I need to put in front of this to cancel out with that 3/2 that I don't want? A 2/3 would do the trick. Now when I differentiate, I get 2/3 times 3/2 x to the 1/2, which is just x to the 1/2. Plug in 1, plug in 0, subtract. That's 2/3 minus 0, which is 2/3. Is 2/3 an answer? No, it's not. So this must be a graph. This kind of looks like the square root graph. We're integrating from 0 to 1, and this goes from 0 to 1, and that's the shape of the square root graph. But I did notice there's another one that looks very similar. It also goes from 0 to 1. So how could I tell which one is actually the square root graph? Let's look at one of the x values. At x equals 0.5, my x value actually, I'm not exactly sure what the square root of 0.5 is, but I do know what the square root of 0.25 is, because that is the square root of 1/4, which is 1/2. So do I see a y value of 1/2 at x equals 1/4? Nope, that's bigger than 1/2. Whereas on this graph, yes, it is exactly 1/2. So this is the graph of y equals the square root of x. So domino I matches with the bottom of this domino. That brings us to this integral, which is definitely the scariest looking integral on this activity. It's not so bad though if you follow the same strategy that we did here, which was simplify the integrand before you try to integrate. The same thing as how we can't integrate the two terms one at a time, we also can't integrate the numerator and denominator, right? For the same reason that the derivative of a quotient is not the quotient of a derivative. But let's simplify this. In the numerator, I see that there's a common factor of x. And when I pull out that x, I'm left with x squared minus 1 over x plus 1. That's a difference of squares, which factors as x minus 1, x plus 1. And that x plus 1 cancels. So I'm left with x times x minus 1. Once again, we should expand that out just like we did here to get x squared minus x. And now I'm going to find an antiderivative. It's 1/3 x cubed minus 1/2 x squared. I'm evaluating from 0 to 1. So I plug in 1, and I plug in 0. And subtract. That comes out to a 1/3 minus 1/2, which is minus 1/6. Now you might think it's a little bit silly that I keep writing out the second term where I plug in 0. In all the examples we've looked at so far, that second term just evaluates to 0. But it's really good to get in the habit of writing it out, even though it's 0, because it's not always going to be 0. It ends up always being 0 when you integrate a polynomial. But when you integrate other functions, if you're not in the habit of writing out the minus capital F of A term, you might forget about it when it actually is not 0. Okay, so do I see a minus 1/6 anywhere? Yes. That was domino C. So we're integrating e to the x plus 1. There are, I can think of 3 different ways to go about finding an antiderivative. If it were just e to the x, we would know the antiderivative is simply e to the x. So the first method is you might just guess that the antiderivative is e to the x plus 1. The chain rule says the derivative of e to the x plus 1 is e to the x plus 1 times the derivative of x plus 1, but that derivative is 1. So in fact, e to the x plus 1 is its own antiderivative. I do want to caution you, though, that that's not... If this were like e to the x squared, this wouldn't work out so nicely. The antiderivative would not be simply e to the x squared, because the derivative of e to the x squared is not just e to the x squared, it's 2x e to the x squared. So, I'm not asking you to be able to just look at this and immediately tell me whether the antiderivative is the same function. I'm just suggesting, guess that it's the same function and compute the derivative and see if that's right. If it is, great, you have an antiderivative. If it's not the same thing, well, then we'll try something else. The second method that I would use to find an antiderivative is that e to the x plus 1 is the same thing as e to the x times e. And that e is a constant multiple. So when you go to find an antiderivative, or evaluate the indefinite integral, you can pull that constant outside of the integral, and then the antiderivative of e to the x is simply e to the x. But I have this constant multiple of e, so it recombines with the e to the x, and I end up with e to the x plus 1. That's another method. A third method is u substitution, which we have not learned yet, but just a little bit of as a preview of u substitution, which we'll cover next week. I would set u equal to x plus 1. I would differentiate, and then I'm going to write that as du equals dx, sort of bringing the dx to the other side, and then this becomes the integral of e to the u, because x plus 1 is u, and dx is du, so that's e to the u du. There's one slight complication here. The bounds change. They're not 0 and 1 anymore. They actually become 1 and 2. But again, this is just a preview. We will see a lot more u substitution. Did I say next week earlier? Not next week, but the week after that when we come back after a break. But really, for all of the integrals that we're doing, all of the antiderivatives, with the exception of the u substitution, we're not really applying any more sophisticated tools than simply recognizing the function as a derivative of something. Like, I just know that e to the x is the derivative of e to the x, and the second method is just making an educated guess and checking the derivative. I think maybe it's e to the x plus 1, so I take the derivative and see if that's right. Okay, I've talked about this problem for way too long, so let's move on. The antiderivative is e to the x plus 1. I evaluate it from 0 to 1, and I get e squared minus e. I don't think e squared minus e appears on any of these dominoes. No, it doesn't. So maybe I'm looking for the graph. This is an exponential function, so it should look like exponential functions do. Ooh, that looks like it's the right shape. But are there any others? This one also looks like an exponential function. How do I decide which one it is? Let's think about an actual value of the function when x is 0. E to the 0 plus 1 is e, which is about 2.7. That's not 2.7. This actually kind of looks like an exponential function, but that's also not 2.7. Yeah, that is 2.7. Okay, so this is the graph. That was domino D. Integral of x plus 1 squared. Okay. By now, hopefully you have an idea of how to go about this. Before I try to find an antiderivative, I'm simply going to expand this out. X squared plus 2x plus 1. Plug in 1. Plug in 0. And subtract. So I get 1/3 plus 1 plus 1 minus a bunch of zeros. That's 7/3. Is 7/3 one of the options? It is! It's right there! So this is domino K. There actually is another way to find an antiderivative. If this were just x squared, you would say the antiderivative is 1/3 x cubed. Maybe the antiderivative is maybe it's just x plus 1, or sorry, 1/3 x plus 1 cubed. Is that an antiderivative? Well, let's just differentiate and check. 3 times 1/3 is 1. It drops to an x plus 1 squared, and I multiply by the derivative of the inside, which is 1. So yes, this is an antiderivative. And that would make this step a little bit easier, because I just plug in the 1 and the 0. I don't have quite as many terms. But once again, just like with the e to the x plus 1, this isn't going to work if the inside of these parentheses is anything more complicated than a linear function. But again, you don't need to know that. Just if you want to make a guess about the antiderivative, just check. See if it differentiates to give the right thing. Okay, so we were on this domino. And the next thing we're doing is the cube root of x. Okay, well, we've seen the square root of x. And what worked there was expressing it with an exponent, so I'll do the same thing here. The cube root of x is x to the 1/3. My antiderivative is going to be something x to the 4/3, because 4/3 minus 1 would get me back to 1/3. And then I don't have any coefficient out here. I guess my coefficient is a 1. So what thing do I need to multiply by so that when I differentiate and I pull down the 4/3, I end up with this 1? Well, that would be 3/4. Plug in 1, plug in 0, subtract. This comes out to 3/4. Is 3/4 an option? No, it's not. So it must be a graph. With the square root of x, we were debating between this graph and this one, and we said that the other one was the square root of x, so this one must be the cube root of x. So this is the domino that matches with domino H. Now we've got the integral of x squared. This is the easiest one we've had yet, because the antiderivative is simply 1/3 x cubed. And it's 1/3. Okay, do I see 1/3? Yes. That was G. Okay, integral of x squared plus 1. I really like to put parentheses around here, because the dx is kind of being multiplied, so anyway. My antiderivative is 1/3 x cubed. We could use the fundamental theorem of calculus and integrate it the way we've been doing. But since we just integrated x squared from 0 to 1, it occurs to me that we can take advantage of that and split this into two integrals. This is one of the properties of integrals. An integral of a sum is the sum of the integrals. We just computed this first integral, it's 1/3, and this is a constant function. Remember what happens when we have a constant function? We end up with a rectangle, so it's just base times height. The base would be 1 minus 0, which is 1, and the height is that constant value of 1. So I get 1/3 plus 1, which is 4/3. 4/3, is that an option? I don't see it, so there must be a graph. That's a parabola. X squared plus 1. That looks like a parabola. This looks like a parabola. And that, oh, okay, well, we already decided that was an exponential function. We've already matched this domino. So, what are some x values? Like if I plug in x equals 0, I should get 0 plus 1, which is 1. Yep, I see 1. But I also see 1 here. So that doesn't rule out either option. But when I plug in an x value of 1, I get 1 plus 1, which is 2. That is not 2, that's 8. And this is 2. So this is the graph that matches with domino F. Okay, integral of 2x cubed. The antiderivative is 2/4 x to the 4th. Evaluate from 0 to 1. Okay, 2/4, which is 1/2. Here we go, 1/2. Domino E. Okay. One half x squared minus minus 2x to the 4th is my antiderivative. And it's always the same strategy. I know that the x cubed is going to get bumped up to an x to the 4th, and I'm just thinking, what do I need to put out in front so that when I multiply with this 4, I get an 8. Plug in 1. Plug in 0. Subtract. Comes out to minus 3/2. There is a minus 3/2. Okay. You could FOIL this out. It would be x cubed plus 3x squared plus 3x plus 1. But you also might guess that 1/4 x plus 1 to the 4th is an antiderivative, and sure enough it is. If we differentiate this, I get x plus 1 cubed times the derivative of x plus 1, which is 1. It works out exactly like it did when the power was just 1 less. Getting a little tired of writing out all of the details of plugging in both bounds. This comes out to 1/4. But 1/4 does not appear here, and I know that because we have seen the graph of this recently. It's going to look like this. The cubic function looks like that, and when we plug in 0, I get 1 cubed, which is 1, and when we plug in 1, I get 2 cubed, which is 8. So I'm looking for a graph that goes up from 1 to 8 as x goes from 0 to 1. That is this one. That was domino L. And we're back to the start. So we have completed the activity. If anyone has questions about any part of this activity, please feel free to drop them in the chat or email them to me. Otherwise, the next thing I want to do is just go over all of the derivative rules that we've learned so far, because that also tells you all of the antiderivatives that you could reasonably be asked to find. Okay, so I'm just going to write down the derivatives of every function that I can think of. We might have a constant function. The derivative of a constant function is 0. And the corresponding fact for antiderivatives would be that the integral of 0 is just c. The plus c is the only part of this. There's nothing else besides the plus c. One of the first things we learned how to differentiate was a power function, x to the n, and the power rule says this is n x to the n minus 1. What if you integrate x to the n? Well, if I differentiated x to the n plus 1, I know it's got to look something like x to the n plus 1, because the power drops by 1 when I differentiate. If I just try x to the n plus 1, I would end up with this n plus 1. I don't want that, so I'm going to divide by n plus 1. So the antiderivative of x to the n is x to the n plus 1 divided by x to the n, divided by n plus 1. And if you go back and look at all of the examples we did in the definite integral Dominoes, where I was like trying to guess what the coefficient should be, for example, when I integrated x to the 1/3, you'll see that it does follow this rule. Although I should point out, this is only true if n is not equal to -1. Of course, it can't be true when n is equal to -1, because that would tell you to divide by 0. What happens when you try to integrate x to the -1? Well, that is one of the derivative rules, or antiderivative rules, that we'll come to momentarily. If you remember back to chapter 3, we covered derivatives of polynomials, so we did the power rule in section 3.1. And in section 3.1 we also differentiated e to the x, and we got e to the x. That means that an antiderivative, or the indefinite integral of e to the x, is e to the x plus c. What if the base is not e? Well, the derivative of a to the x is also a to the x, except you also have to multiply by the ln of a. I wanted to say something about this. What was it? Oh, I just wanted to emphasize that there's a huge difference between these things. This is a common mistake I see. This is a power function, the variable is in the base. This is an exponential function, the variable is in the exponent. These are completely different functions. You cannot use the power rule on an exponential function. You cannot use this derivative rule on a power function. Like, the most common mistake I see here is something like the derivative of e to the x is x e to the x minus 1. You're trying to apply the power rule, but it does not make any sense to apply the power rule to e to the x, because that's not a power function, it's an exponential function. It's a completely different kind of function. So just be careful with that. What if we integrate a to the x? So you might guess that it's a to the x plus c. And then to confirm if that's right, you would differentiate this a to the x and see if you get a to the x. But that's not right. We're going to get a to the x ln of a. But I just want to get a to the x, so I need to divide by the ln of a. So if I want something whose derivative is a to the x, I should take a to the x divided by the natural log of a. you might start to see a pattern, which is that when we differentiate a power function, we end up multiplying by something. When we differentiate, or when we anti-differentiate a power function, we end up dividing by something. By the same thing, actually. It doesn't look like the same thing, because here it's an n, and here it's an n plus 1, but the point is, in both cases, that number matches the exponent of the antiderivative. And that n matches the power that was being differentiated. Same thing down here. When we differentiate an exponential function, we end up multiplying by ln of a. When we anti-differentiate an exponential function, we end up dividing by the natural log of a. Okay. What about the inverse function of these exponential functions? The inverse function of ln of x is... Sorry, the inverse function of e to the x is ln of x. The derivative of ln of x is 1 over x. Note, that's equal to x to the minus 1. This is where that missing case happens. When the exponent is negative 1, you don't end up with another power function. You end up with 1 over x. Or, sorry, the natural log. And there's a slight subtlety, which is that you don't just get the ln of x, you get the ln of the absolute value of x. Why? Well, because ln is only defined when x is positive, but 1 over x is defined for all positive and negative x values, just not 0. So by putting in these absolute value signs, we end up with a function. We end up with an antiderivative which works for all x values except 0. The inverse of the exponential function with base a is called log base a, and the derivative of this is 1 over x times the ln of a. And there's not really a corresponding rule for antiderivatives, because if you were ever given this thing and asked to integrate, you should just say that 1 over ln of a is a constant multiple, so it comes outside of the integral. And you're left integrating just 1 over x. And then you might notice that the ln of something divided by the ln of something else, one of the derivative rules says that this is log base a of the absolute value of x. Okay, now let's get into trig functions. The derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. The derivative of tangent of x, and the good news is that if you've memorized these two derivatives, you don't necessarily need to memorize the derivatives of the other 4 trig functions. It might be convenient to memorize the derivatives of the other 4 trig functions just so you can recall them quickly in case it comes up on the final exam. But in principle, you can deduce any of these four from these two using the quotient rule. So it is not the end of the world if you forget one of these. The derivative of tangent x is secant squared x. The derivative of cotangent, and as a shortcut to memorization, when you have a pair like tangent and cotangent, the derivatives are they do the same thing of putting a co in front. So secant squared becomes cosecant squared, and we also throw in a minus sign. That rule actually applies here also. The derivative of sine is cosine, so the derivative of cosine is, well, I guess I said you add on a co, so instead of cosine it would be cosine, but if you think of the co's as canceling out, like, sort of, anyway, but you also get a minus sign. And the derivative of secant of x is secant of x times tangent of x. Make sure that you're always writing the of x. I often see things just like secant tangent, but that's not correct. You do need the x, and the reason why it's dangerous to be a little bit lazy and not write the of x is because this is ambiguous. Do you mean secant of tangent of x, or do you mean secant of x times tangent of x? So always write the of x when you have trig functions. Any kind of function, really. Not putting the of x is like, it's kind of like writing f of, but not actually putting anything inside the parentheses. Okay, so if I follow my rule, where I go from secant to cosecant, I'm going to change that secant to a cosecant, I'm going to change the tangent to a cotangent, and then throw in a minus sign. So these are the derivatives of all 6 trig functions. Now the corresponding rules are that the integral of cosine of x is sine of x plus c, and the integral of sine of x is minus cosine of x plus c. There are also antiderivatives for the other 4 trig functions. You'll learn about them in Calc 2. It is not a topic for Calc 1. And of course, if I just told you what any of these antiderivatives was, you could take the derivative and check that it actually is the antiderivative. But coming up with the antiderivatives is a little bit tricky. I'll tell you one of them, just for fun. The antiderivative is the antiderivative of tangent of x is the ln of the absolute value of cosine of x over sine of x plus c, I think. No, sorry. It's the ln of the absolute value of 1 over minus the ln of 1 over see what I mean? This is confusing. This is confusing. But it's worth pointing out, what am I doing? I'm doing the exact same thing that I told you all to do, was make educated guesses and then check the derivative. So I'm writing down what I think it is, and then computing the derivative in my head and realizing I'm wrong. But then that gives me an idea of how to make it my next guess. So it's minus ln of the absolute value of the cosine of x. Do you see what I mean? Like, you could compute the derivative of this thing with what you know from Calc 1, but how would you come up with that? U substitution, actually, is the answer. Anyway, and I'm erasing that because I don't want anyone watching this to get the idea that you need to know the antiderivative of tangent. So we also have inverse trig functions. Arcsine of x. The derivative of arcsine of x is 1 over root 1 minus x squared. And the derivative of arctangent of x is 1 over 1 plus x squared. The other 4 inverse trig functions, of course, also have antiderivatives. I wouldn't worry about them. You know, for the sake of completeness, I'll put in 2 of the others. Just because they're really not that bad. The derivative of arc cosine of x is the same as the derivative as arc sine of x, except there's a minus sign. And the same is true for tangent and arctangent and arccotangent. It's the same as the same derivative, but with a minus sign. And then the corresponding derivative rules, or antiderivative rules rather, are simply that if you're ever asked to find an antiderivative for 1 over root 1 minus x squared, that looks complicated, but you just say, wait, nope, I recognize that as the derivative of arcsine of x. Now you might also notice I can just pull the minus sign outside, and that would lead me to minus arcsine of x plus c. And now maybe you're thinking, is arc cosine really just the opposite of minus arcsine? Almost. They're not equal, they differ by a constant. So I have these plus c's here. So when you have 2 expressions with arbitrary constants in them, if those expressions are equal, it doesn't mean these things are equal. It means that they differ by a constant. And the idea is that sine and cosine look the same, the graphs look the same, except they're shifted by pi over 2. So when you take the inverse function, the inverse sine and cosine functions are the same, except they're shifted vertically by pi over 2. Okay, so the antiderivative of 1 over 1 plus x squared is arctangent of x plus c. The antiderivative of minus 1 over 1 plus x squared is arccotangent of x, or simply minus arctangent of x. plus c. Okay, so this is a pretty complete list of all the functions that you know about, or rather, it's the building blocks of all the functions you know about. You can also add any two of these together, or multiply by a constant multiple, or subtract two functions, or compose them, or exponentiate, or multiply, or divide. So we also have some rules that tell us how to combine functions together. The derivative of a sum of functions, for example, is the sum of the derivatives of the functions. And the derivative of a difference is the difference of the derivatives. And the same is true for antiderivatives. The integral of the sum is the sum of the integrals. And the integral of a difference is the difference of the integrals. The derivative of a constant, the constant multiple, is that constant multiple of the derivative. Constant multiples come outside of derivatives. They also come outside of integrals. When we differentiate a product, we don't just get the product of the derivatives. The product rule says we get f prime of x times g of x plus f of x times g prime of x. Now, just as the derivative of a product is not the product of the derivatives, and I've already talked about this at the very beginning of the review session, an integral of a product is not equal to a product of integrals. If you want to integrate a product, it's a little complicated, and this is a Calc 2 topic. But there's a technique called integration by parts, which is used to integrate a product. When we differentiate a quotient of two functions, the quotient rule says we get, the mnemonic device I use is low D high minus high D low. Draw the line and square below. It is very important what order these terms go in. In the product rule, it does not matter what order you write these in because addition is commutative. Subtraction is not commutative. It matters which term comes first. There's not really a corresponding rule for antiderivatives. You can try to write something down in the style of integration by parts, but it doesn't really end up being useful. Another way that you can combine two functions together is by composing. And the chain rule says that the derivative of f of g of x is f prime of g of x times g prime of x. There is a corresponding rule for antidifferentiation, And the way that you should think of this as integration by parts is kind of used to undo the differentiation of a product. So what is used to differentiate or to undo the differentiation of a composite function? It's U substitution. Which we will cover after break. But feel free to Google or search on YouTube for Khan Academy U substitution, or read the textbook. Work ahead, start learning about U sub, just so that you're not having to learn this for the first time in the week before the final exam. If you have time over break to look ahead, it certainly could not hurt. The only other way to combine two functions together that we have not already touched on is exponentiation. When you differentiate f of x raised to the g of x, you get that same thing back times g prime of x ln of f of x plus g of x f prime of x over f of x. Do not memorize this. The way that you should actually compute a derivative like this is using logarithmic differentiation. And one reason you should not memorize this is that I just wrote this down by trying to do the logarithmic differentiation in my head, and I'm not, I wouldn't bet my life that I didn't make a small mistake somewhere in here. But the point is, you can use logarithmic differentiation. The idea is that you write y equals f of x to the g of x. You take the ln. A rule of exponents says the g of x comes outside. And now you implicitly differentiate this. So that's the strategy. Alright, I think that concludes my list of all of the derivative rules that we've covered throughout Calculus 1 and all of the corresponding anti-differentiation tools and techniques. I'm going to pause here for a moment. If you have questions, now would be a great time to throw them in the chat. Where's the donate button? My channel is not monetized. Doing this just because I want to help you all out, and I really enjoy talking about math. If you want me to be able to monetize the channel, I need to get 25 followers, I think. So drop me a follow if you have not already done so. I don't really drink coffee. That's the thing. But again, just doing this to help you all out. If you all find this useful as you're preparing for the final exam, that's all I need in return. So, if there are other topics you'd like me to cover, send me a message. But again, I'm watching my email if you don't have a Twitch account. But I think maybe, unless there are any suggestions, I'll just do one more optimization problem. I did one on Monday, but optimization is one of the hardest topics we cover, so it could be helpful to do another example. And I found a cool example that I will want to tell you about. So let's do that, and then if there aren't any other suggestions, we'll call it a night after the optimization problem. NNNAA100, thank you for the follow. So here's my optimization problem. So I'm at 18 followers now. Just need 7 more, so tell all your friends to follow me. So the optimization problem I want to look at is we're going to find the length of the shortest ladder that will reach over an 8-foot high fence to a large wall which is 3 feet behind the fence. So, if you're in my class, you know that the first thing I always want to do in an optimization problem is to draw a picture. I'm actually even going to try to draw this one to scale. So let's say here's the wall. And there's a fence which is 8 feet high. And the wall is 3 feet behind it. I think I actually need to make this a little bit taller. So let's move this down to the next page. So when they say a large wall, they mean it's very tall. And the point is that you're over here. Okay, you're not to scale because I guess I just drew you about 2 feet high. But you're going to put a ladder. You're trying to get to the wall. for some reason you're trying to climb over this ladder. Okay, I'm going to race you. And the ladder has to touch the ground, of course. It has to rest on the ground, and we want it to extend all the way to the wall, and it's got to go over the fence. So I first like to sort of just picture what are some different possibilities, just to kind of convince myself that maybe there even is a maximum. Like, what if I start out really close to the wall? I'm going to have a really long ladder because it's going up at such a steep angle that by the time it moves another 3 feet over to the right, I'm going to be very high up. Or I could start very far away. I could put the base of the ladder on the ground very far away from the fence. Like over here. And then you see I'm going to hit the wall not very high above the fence, but this is a really long ladder. So somewhere in between these two extreme possibilities, there should be a minimal length. And that's what we're going to try to find. I just think this is a really cool problem. So if you remember, or if you watched the previous review session, the next thing I thought about after I drew the picture was, what's the thing I'm trying to optimize, and what's the thing that I can control? We are trying to minimize the length of the ladder. And what we can control is, well, what was I changing here when I drew these different possibilities? I was changing how far the base of the ladder is from the fence. So if that's the thing I can control, I should make a variable for that. I'm going to call this x. So this is x. And then while I'm labeling things, I noticed that this is just 3 more feet. So this is x plus 3. I guess I should also label the height. The height of the fence. We're told that it's going to be important. I also want to mention I have not actually worked out the solution to this problem before. I'm doing this on the fly, mainly because I wanted you all to see, like, genuinely how I approach an optimization problem. I'm not telling you to draw a picture just because I want you to for some obscure reason. No, that's like actually how I solve a problem. It is really helpful to draw a picture. Okay, so I've started to label some things, and I started labeling based on thinking about what's the thing that I get to control in this scenario. So now I'm going to try to think a little more about the thing that I'm trying to minimize, which is the length of the ladder. Now this is a right triangle, and I already know the base is x plus 3. So if I knew the height, then I could use the Pythagorean theorem to find the length of the ladder. So the height is a quantity worth thinking about. And I specifically mean the height of the top of the ladder above the ground. I'm going to call that h for now. Obviously, I don't want h in my final equation because I always want my function to just have one variable, and I want that one variable to be the thing that I can control. But it might be helpful to label this h for now. And I hope you see how I came to the realization that I should label this. It's because I'm trying to find the length, which is this, and I see a right triangle, and I think Pythagorean theorem. This side is going to be important. Okay. So I need to find h in terms of x. So it's helpful to look at the quantities we've labeled so far to try to think about how we could relate them. I've labeled these two sides of that triangle, and I've also labeled these two sides of this triangle. So when I'm thinking about four sides of two triangles, and in fact these aren't just any old triangles, these are similar triangles. When I'm thinking about side lengths of similar triangles, that makes me think I should use what I know about similar triangles, which is that ratios of corresponding side lengths are proportional. So because we have similar triangles, I can write down the equation 8. You know what? I don't want my variables in the numerator, so I'm going to go x over 8 equals x plus 3 over h. Right, so the left-hand side is this triangle. The right-hand side is the big triangle. The numerators are the bases. The denominators are the heights. Right. So base over height has to equal base over height when you're dealing with a right triangle. Let me draw that a little more carefully. Base over height equals base over height. Okay, so I want to know what h is, so I'm going to try to rearrange this equation to get h by itself. I did this by cross multiplying, so xh equals 8 times x plus 3, and then just divide by x. There we go. H is going to be equal to 8 times x plus 3 over x. Now that I know the height, why did I do that? It was because I thought that would be helpful in finding the length of the ladder. I'm going to call this L as a function of x, and it's the square root of, well, I'm looking at this triangle, so I have x plus 3 and h as the legs of that right triangle. So it's the square root of x plus 3 squared plus this. 8 times x plus 3 over x squared. Now there's a really neat idea that would make the algebra and the calculus quite a bit easier. I'm going to try to do it the hard way, because this is an insight that's maybe a little bit difficult to just have while you're trying to solve a problem. And I want to make sure that we actually can do this without just having this really nice, helpful insight. But the insight is that minimizing the length is the same as minimizing the length squared. The longer the length is, the longer L squared is. And the longer L squared is, conversely, the longer L is. That's helpful because if you square this, you get to get rid of the square root, which means that you don't need to deal with square roots when you differentiate. So, that just simplifies the calculus and the algebra. But we're not going to use that observation. We're gonna do this the hard way. This is my function. I'm going to I'm gonna differentiate this. I'm differentiating because once I have the function, I'm looking for critical numbers. The derivative of the square root of something is 1 over 2 times the square root of that thing. Ooh. You know what? I actually want to simplify. I'm afraid that I'm going to have to do a quotient rule with this x plus 3 over x, but I'm noticing that if I just distribute that 8 and then simplify, distribute the 1 over x, this is going to be 8 plus 24 over x. So I think that's going to make our life a little bit easier. Okay, so the derivative of square root of something is 1 over 2 times the square root of something times the derivative of that something. That is the chain rule. Okay, derivative of x plus 3 squared. I could FOIL that out, but I can also just use the chain rule. It's 2 times x plus 3 to the 1, using the power rule, times the derivative of the x plus 3, which is just 1. And then the same thing here. It's 2 times 8 plus 24 over x times the derivative of the 8 plus 24 over x, which is minus 24 over x squared. That's complicated. You should not expect something this complicated on the final exam, but I think it's really valuable to look at hard problems when we're reviewing, because it is still the same ideas, the same techniques, the same tools, same strategies, and it's just good practice. Right? The harder the problem is, the more practice we get with like algebra and differentiation rules. And you will need to use all of these ideas on the exam, even if you don't have to use quite so many of them all at once. So I'm looking for places where this is 0 or undefined. Now this thing is never 0. You can never divide 1 by something and get 0. We could make this undefined if the numerator is 0. Or the denominator is 0. So, could I ever make that denominator 0? Well, the denominator would be 0 only if the thing inside the square root is 0, but that's something squared plus something squared. When you square things, it makes them positive. When you add positive things, you get positive things. You don't get 0, unless both of these are both 0. The only way that this could be 0 is if x is negative 3. If x is negative 3, I get 0 squared plus 0 squared. Sure enough, x equals negative 3 does make this denominator 0. But x equals negative 3 would correspond to putting the base of the ladder here, which is obviously nonsense, right? The whole point is that we're over on this side of the fence. We have to start the ladder over to the right side of the fence. But I guess the mathy way to say that would be that x equals negative 3 is not, or I guess negative 3 is not in the domain of our function. And I'm thinking about all of this because I'm looking for critical numbers, which would happen when the function is undefined or when it's 0. We've just thought about where it's undefined. Now I'm going to think about where L prime of x equals 0. We just said 1 divided by something can never be 0. So the only way the entire derivative is 0 is if this piece is 0. So we're going to need 2x plus 3 plus 2 times 8 plus 24 over x times minus 24 over x squared to be equal to 0. The first thing I'm going to do is add that term over to the other side. So I'll get 2x plus 3 equals 2 times 8 plus 24 over x times 24 over x squared. And the minus sign is gone because I added a copy of this to both sides. A copy of this. The 2's cancel. That's nice. How do you solve this? So when I look at an equation like this, one of the first things I think is I have some x's in the denominator. That annoys me. I don't like having the variable in the denominator. So I'm going to multiply both sides by enough x's to cancel out all of the x's in the denominator. And on the left side, I'll need 2 to knock this out, but I still will have 1 more x in that denominator, so it'll actually take 3 x's to get the job done. So here I'll be left with 8 plus 24 over x times 24x. So I took 2 of these 3 x's to cancel out that x squared, and that just leaves this 1x. When I multiply 8 and 24x, I get 192x. And when I multiply 24 over x by 24x, the x's cancel and I get 24 squared, which is 576. I'm going to double check. 576. Yep. Oh. Does this... Yes. Okay, this does factor nicely. I was getting a little worried because this is going to be a 4th degree equation. But it maybe shouldn't surprise me that it does end up factoring nicely, because these optimization problems tend to have nice solutions. If you're trying to maximize the area with a given perimeter, it ends up with a really nice solution where the perimeter is equally distributed among all the sides, which is to say you get a square. I notice I have a common factor here. Really what I noticed, really what I thought, it was wishful thinking. I saw an x plus 3 here. I was really hoping that I could get an x plus 3 over here. So I thought, what's 192 times 3? And sure enough, 192 times 3 is 576. So if I factor out 192, I'm left with x plus 3. Now at this point it's tempting to cancel out the x plus 3's. You really shouldn't cancel things with x's in them like that, because that could it could destroy a solution. Essentially, -3 is a solution to this equation, but after you cancel the x plus 3's, -3 is no longer a solution. So when you cancel things with x's, you actually destroy solutions sometimes. Now, in this case, that's not much of a problem because -3 is not in the domain, so -3 is not a solution that we're looking for. But so you could get away with it here, but I want to do this properly. It's just a good practice to not cancel. What you do instead of canceling is you factor. I bring everything to one side of the equation. I factor out the x plus 3. I'm left with an x cubed minus 192. So x is -3, and we already said -3 is not in the domain. Or the other solution is x cubed is 192, so x is the cube root of 192. So that should be our critical number. Just for the sake of making sure that this seems reasonable, I'm using a calculator to get a decimal approximation. It's about 5.8. Does that look reasonable? So that would start 5.8 units away from the wall, which is about here. That looks pretty reasonable. I'm convinced that it is shorter than the black line that I drew here. Like, these are about the same, but here the blue line definitely seems shorter than the black one. Okay, cool. So, as always, if you're given oh, I lost my train of thought. If you're given an optimization problem, you will probably be asked to justify that you have actually found the absolute maximum. So this is a critical number. That's what we were doing, remember? We were solving for the critical numbers. And it turns out this is the only critical number. But how do we know that this critical number actually gives the absolute minimum? Right? Sometimes critical numbers are maxima instead of minima. Sometimes they're neither maxima nor minima. We want to make sure this one's actually an absolute minimum. It's the only critical number, so if it's a local minimum, it is also the absolute minimum. So we would just want to argue that this actually is an absolute minimum. Sorry, we want to argue that it's a local minimum. I'm starting to space out a little bit. It's probably about time to wrap up the stream. But just how would we do this? I would make a sign chart. So here's my sign chart. The thing that we're analyzing the sign of is the derivative, L prime of x, and we're splitting it at the cube root of 192. To test the sign, I should just plug in something less than 192, or less than cube root of 192, and something greater than the cube root of 192. 1 is definitely less. Less than the cube root of 192. And L prime of 1 is, oh boy. Well, this is positive, so I don't even have to worry about this. If I plug in 1 here, I get 6. And this is 24 plus 8 is 32, so that's 64 times negative 24. That's huge. This is a huge negative number. That 6 is not going to make it positive. So this is negative. And again, to be clear, this is the details that are messier than anything we would give you on the final exam. What's something greater than the cube root of 192 I think 8. 8 is a good choice. I'm thinking of 8 because the x has to divide 24. Well, 24 gets divided by x. You could plug in things that don't divide 24 evenly, but this is going to be easier for me to do in my head if I pick a number that divides 24. And 8 is definitely bigger than the cube root of 192, and I know that because I'm a bit of a nerd, so I've memorized the perfect cubes of some number of integers, and I know that 8 cubed is 512, which is bigger than 192. So when I plug in 8, I get again, all positive. Here I'm going to get 22, and here I'm going to get, this is 11, so that's 22. Well, this thing is 22, but this is minus 24 over 64. That fraction is less than 1, so this whole thing is less than 22. And what I really mean is it's greater than negative 22. I don't know why I'm doing this. Just use a calculator. But I've convinced myself that it's positive. So the sign chart looks like negative to positive. And the first derivative test tells us that if the first derivative goes from negative to positive, that means your function is going from decreasing to increasing. That's a local minimum. And the last thing that I need to write to establish that it's an absolute minimum is just that since the cube root of 192 is the only critical number, it's also an absolute minimum. All right, we are done. Turn one nut Peggle, were you suggesting when you said 6, were you suggesting a number to plug in that's greater than the cube root of 192? If so, that's an excellent choice. Arguably the only other good choice besides 8. And what are the important properties? Well, it's a whole number. It evenly divides 24. And it is bigger than the cube root of 192 because 6 cubed is 216, which is just barely bigger than 192. So actually, yeah, 6 would be an excellent choice to plug in if you had to do this by hand. Any other questions before we call it a night? Six, also the number of viewers we have at the moment. So, while I'm waiting for questions, anyone in chat, anyone doing anything fun over winter break? You can answer that question too, but I meant Thanksgiving break. Anyone going anywhere cool? I am planning to road trip out into Utah, visit some of the national parks, do a little bit of camping. If you haven't been out to like Moab, Canyonlands, Arches, highly recommend. Bryce Canyon is maybe my favorite national park in Utah. Alright, well, I see no questions in chat, so let's call it a night. Thanks for joining. The recording will be accessible on Twitch for the next week. And I will also put it up on YouTube, but that might not happen immediately. So have a great break. I'll run some more sessions when we get back from break. Probably on the Sunday before we start up again, or maybe the Monday or Tuesday back from break. So have a great break. Thanks for joining, and I will see you next time. How do I end the stream? Oh yeah, I remember.